We have previously implemented our own Fourier transforms in 2 dimensions for image processing. Now it's time to look at some libraries that implement fast Fourier transforms. NumPy, SciPy, PyTorch, and OpenCV and others have fast Fourier transforms. Each are optimized for a different purpose. NumPy is good for general purpose applications. It's easy to use. SciPy is faster and more flexible. It's preferred for scientific use. PyTorch, as expected, is optimized for deep learning and is GPU enabled. OpenCV's implementation is optimized for image processing, and that's what we're going to focus on in this coding demonstration. Specifically, we're going to use OpenCV's discrete fast Fourier transform and inverse fast Fourier transform to map back and forth between the spatial and frequency domains and demonstrate that such transitions are lossless. The coding demonstration is in this Colab notebook, and you will have a link to this in the description of this video. So let's open the notebook. So here we are. We import CV2. Here we just load the image of a cat. This is very important. OpenCV's Fourier transforms expect the image to be in a float 32 data type, so it's important to cast your image to that data type. Then you simply call CV2's DFT function, which is the direct Fourier transform for its 2-dimensional fast Fourier transform. And you give it the image in its float with its float data type. And this is also important. You have to set this flag. It doesn't do it by default. And what this flag says is that give me the complex output, that is both the real and imaginary components of the Fourier transform. And that's exactly what you need in order to do all the things you want to do, including displaying the magnitude spectrum. So here's your Fourier transform. Let's look at its shape and compare it to the shape of the image. The shape of the image is this, 778 by 584. The shape of the Fourier transform is the same, except that it has 2 channels. One channel contains all the real components. The other channel contains all the imaginary components. So if you were to look at the value of the Fourier transform at a particular horizontal and vertical frequency, in this case 0 and 0, you would get a complex number with a real component and an imaginary component, which is exactly what you want. So now if you want to compute the magnitude at that particular frequency, you know that you square the real component and the imaginary component, sum them, and take the square root. But in fact, you don't have to go through that trouble because OpenCV has a function that does it for you. So here we show how that's done. You extract the real component from the 0 channel. You extract the imaginary component from channel 1. And then you call CV2's magnitude function. You give it the real and imaginary components, and it gives you the magnitude spectrum. Except that this raw magnitude spectrum, you don't want to display it, and this is the reason. Let's print the maximum magnitude, the minimum magnitude, and the ratio of the two, and this is what you would get. The maximum magnitude is about 60 million. The minimum magnitude is about 6. And the ratio is 10 million. So if you were to just plot the raw magnitude spectrum, you would end up with a tiny single bright pixel representing the DC component in the center, and everything else would be black because of the large difference between the high frequency and the lower frequencies. This is why you want to take the log of the magnitude, and you also add a 1 here in order to avoid taking the log of 0. So this gives you the magnitude spectrum that you can display. and now we're going to display it. This is what you end up with after you take the log. You will notice that you have a bright spot here, 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 and here. And this is actually the DC component. It turns out that both NumPy and OpenCV put the zero frequency bin at coordinate 0, 0. That corresponds to the DC component being here. And of course, that's not the convention that we have talked about. We want the DC component to be in the center. So we need to shift it from this corner to the center. And NumPy offers a very simple function that achieves that for you. It's called FFT shift. So you give it the output of the Fourier transform function, and it shifts it to the center. Now that you have properly shifted the Fourier transform, now you can go through the same process, take the real component and the imaginary component from channels 0 and 1 respectively, compute the magnitude using CV2's magnitude function, take the log, and now display your magnitude spectrum. And now you will see that it's properly displayed with the DC component in the center. The surrounding coordinates correspond to the low frequency smooth areas of the image, and the more peripheral frequencies correspond to the detail and texture and noise in the image. All right, so now we have a proper and properly displayable magnitude spectrum. Can we reconstruct the image from this, from our Fourier transform? And of course we can, but first we have to unshift it. Remember, we had previously shifted it, so this is our shifted or centered Fourier transform. We have to unshift it, and again, NumPy offers a function called inverse fast Fourier transform shift that inverse shifts or unshifts it. And now that you have unshifted it, you can submit that to CV2's inverse Fourier transform to reconstruct your original image. There are two flags that you need to set over here. The first is this flag here, DFT scale. Remember, the formula for inverse Fourier transform normalizes or scales the image by dividing by the number of pixels, and this is what this flag achieves. The second thing is that you're only interested in the real component of the output now, because you're back in the spatial domain and you don't care about the imaginary component, and that's what this flag says. So now that you have your image reconstructed, you can display it. This is the original image, this is the reconstructed image. They look identical, and we can compute the root mean square error between the two images. We subtract the images, square them, mean them, take the root, and print that, and that's a very small number, close to 0, and that corresponds to the floating point error in this process. But essentially going back and forth between the frequency domain and the spatial domain is lossless.